So with the dry ice puck lab, you had a dry ice puck on a ramp, and as you saw in the video, the dry ice would sublimate into carbon dioxide gas, and it would escape out underneath the puck. But what that would do is lift the puck off the ramp a little bit so that there was pretty much no friction as it slid down the ramp. So you did an experiment where you're going to describe the motion of a couple of those pucks, and you probably came up something with something that looked like that. Now I know you did two of them, but let's just focus on one for now. And what claims can you make about the puck when you look at this graph? Probably some things you thought about were things that you focused on last unit when you talked about discussing motion, where you'd say, hey, where does it start? And you could look at this graph and say, hey, it starts at position 0. And then you'd probably say something like, oh, which direction did it move? And you'd say, oh, it moves in the positive direction. And then we said, what type of motion does it have? And we used to say, oh, it has a constant velocity or a constant speed, or it moves with uniform motion. But we can't really say that about this puck, because when you look at the graph, it shows something different than our uniform motion examples in the past have shown us. And so what you can see from this graph is that it looks like the puck is speeding up. How do you know that? Well, back in our previous unit, when we talked about uniform motion, we looked at a graph of position versus time, and that graph looked like something like that, where the graph would be linear. And we said, hey, the reason it's linear is that if you pick some times in here, so we say, hey, look, for equal changes in time, right? For equal changes in time, you get equal changes in position. So equal changes in time, you get equal changes in position. But if you look at this graph, on our position time graph, and we say, hey, look, let's pick equal changes in time. So here's delta t, delta t, delta t, delta t. For equal changes in time, what happens to the change in position? Let's take a look. We have something like that, and something like that, and something like that. So I think you can see that the changes in position are increasing. The displacement is increasing with every successive equal-sized time interval. And that is pretty much telling us that the rate of the change in position with respect to time is changing, or that the velocity of the puck is changing as time goes on. So let's focus on this position-time relationship for the puck. Back in our uniform motion unit, when the graph looked like this, we said, hey, the position is directly proportional to the clock reading, which means that if the clock reading changes by a certain factor, then the position is going to change by the same factor. Kind of like if I'm making cookies and I have a recipe that calls for 2 eggs and a stick of butter, but I look in the kitchen and I only have half a stick of butter, then I can still make the recipe. I just have to change everything else by that same factor of a half. So I just use 1 egg instead of 2 eggs, and I'm good. So if the clock reading, say, doubles, then position doubles. Okay. But when you look at this graph, when you look at the position time graph for the dry ice puck, you can see that position and the clock reading are not directly proportional to each other. That if you double the clock reading, you're going to more than double the position. So how do we analyze this curved graph? In this class, when we do the mathematical analysis, we're using a linear equation to do all of our analysis. This is not a line. And so what we do is we're going to linearize the graph by manipulating our data a little bit. We're still going to use the same variables, position and clock reading, but we're going to play around with the math of them a little bit so that we can make a graph that comes out to be linear. And if you look at this graph, you can see that you're getting increasing changes in position for equal changes in time. In other words, when this changes by a certain amount, this is changing by more and more and more and more. So you need something on the x-axis. We need to do something to the clock reading that's going to kind of stretch out this axis a little bit and make it more and more and more and more. And it turns out that the thing that does the trick is to square the clock reading. So if you make a graph of position versus t squared, then one thing you notice is it crams all your data points in over this portion of your graph. But what you end up with is a graph that is a line. Okay. So now we have a line with 0 y-intercept on the graph, which tells us that the position is directly proportional to not the clock reading, but the square of the clock reading. So what does that mean? It means whatever factor t squared changes by, position changes by the same factor. So let's say we've got, say if we've got a t of 1, we've got a position of 1. If we've got a t of 2, what's my position? Hopefully, you guys are thinking that, oh, we need to make an extra column here for t squared, and this goes, t squared is 1, 2 squared is 4. So that means that my t squared is changing by a factor of 4. Hey, when I say factor, I mean I'm multiplying it by 4, right? So that means that my position must also change by a factor of 4, which means that my position must be 4. So if my position doubles, if my clock reading doubles, my position is actually going to quadruple. Okay. So what if my clock reading changes by a factor of, I don't know, 3? What does my position change by? So in other words, my clock reading goes from 1 to 3. Then my position goes from 1 to what? Hopefully you see that t squared is 9 here. So this is a factor of 9. Which means that my position must also change by a factor of 9. Which tells me that my position is going to be 9. Alright? Okay, here comes our next example. Let's say that at a clock reading of 1, my position is 5. Then what if my clock reading changes to, I don't know, 10? Then what is my new position? Hopefully, you guys can see that we make a little column for t squared. 1 squared is 1, 10 squared is 100. So thinking proportionally, if t squared is changing by a factor of 100, then my position must also change by a factor of 100, which tells me that my position now is 500. Cool? So let's look at what the mathematical analysis looks like for this kind of graph when we do the linearizing. So we've got t is clock reading. We're defining our variables, right? we've got x with the arrow is the position. And if we're looking at a model, a linear model of y equals mx plus b, then we've got the position equals k times the t squared plus b. So what I'm looking at there is, on the y-axis I've got position, on the x-axis I've got t squared. Then, real quick, I can say, hey look, the y-intercept of this graph is 0. And then I need to look at the slope. So I'm going to calculate the slope. Slope is the change in position over the change in the t squared. And then you can plug in some stuff to figure that out. Pick 2 points on the graph, blah, 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 right? And you're going to throw in some numbers, blah, 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 blah. And you'll end up with k equals something, and most of you probably got somewhere around, I don't know, 0.17-ish, maybe a little more, maybe a little less, centimeters per square tick. And then we write our specific model. Position equals 0.17 centimeters per tick squared times t squared plus 0. Now, here's the weird question. Is this mathematical model, does this describe the graph of position versus time squared? Or does it describe the graph of position versus time? So what's this model for? Is this mathematical model describing the graph that you made with your raw data or the linearized graph? All right, hopefully you guys came up with the right answer, which is it describes both graphs. And that's the beauty of looking at our graphs and linearizing data like this, is that we can have a curved graph, which is kind of a pain to analyze. But if we can get the data to linearize, then the equation that we come up with will describe both the linearized graph and this curved graph that we have. Our next step would be to look at this mathematical model and try to generalize. But we can't really do that quite yet. Okay? Right now we know that slope tells us something about the rate of change in position with respect to the time squared. And what it's telling us is that for every square tick of square clock reading, the position changes by 0.17 centimeters. That's kind of weird because you can imagine what a square inch looks like and what a square foot looks like, but it's hard for me to think about what a square second or a square tick looks like. I don't know if you can do it or not. So we're not going to focus on that right now, and we're not going to generalize that. We'll come back to that in a couple days.